4 billion years ago, Mars was a very different world. Rivers carved through its surface, lakes filled ancient craters, and there may even have been vast seas or an ocean across its northern lowlands. Today, Mars is cold, dry, dusty, and almost completely hostile to life as we know it. So, what happened? How did a planet that once had liquid water become the frozen desert we see today? And perhaps the more important question, why didn't the same thing happen to Earth? This is the story of how Mars lost its atmosphere, lost most of its surface water, and slowly became the red planet we know today. Mars is the fourth planet from the Sun. It's about half the diameter of Earth, and only around 10% of Earth's mass. Its day is surprisingly familiar. One Martian day lasts about 24 hours and 37 minutes. But billions of years ago, Mars looked dramatically different from the world we see today. We know this isn't just an artist's imagination. The evidence is written into the rocks. Across Mars, scientists have found ancient valley networks, river channels, lake sediments, deltas, and minerals that formed through interaction with liquid water. And one of the most important places we've found is Jezero Crater. That's where NASA's Perseverance rover landed in 2021. Jezero once contained a lake. A river flowed into it and built a delta. And today, Perseverance is driving across those ancient sediments, drilling rocks and collecting samples that could preserve clues about the planet's ancient environment. Mars wasn't necessarily a second Earth, but it was once a world with environments that could have been habitable, and that changes everything. The evidence for ancient water is everywhere. Dried-out river valleys are stretching for hundreds of kilometers. There are ancient lakebeds inside impact craters. There are mineral deposits that form when water interacts with rock. And some features have even been interpreted as possible ancient shorelines. These observations have led scientists to propose that Mars may once have had enormous bodies of water in its northern lowlands. But there's an important distinction. The idea of an ancient Martian ocean is plausible, and there is geological evidence supporting it. But the exact size, depth, and even the precise shape of its shoreline are still debated. So we shouldn't imagine Mars as a perfect blue copy of Earth. The real picture is probably much stranger. Mars may have gone through periods when liquid water was widespread, followed by periods when the planet became much colder and drier, and eventually the warm and wet conditions became much harder to maintain. So what changed? The first major clue is hidden deep inside the planet. Mars is small, and size matters. A smaller rocky planet loses its internal heat faster than a larger one. Billions of years ago, Mars had a global magnetic dynamo generated by movement inside its metallic core. That dynamo produced a global magnetic field. Earth still has one today. Mars doesn't. Instead, the planet is left with only patches of ancient magnetism frozen into parts of its crust, along with an induced magnetic environment created by its interaction with the solar wind. And this difference was critical, because the magnetic field wasn't just a compass for ancient Martians. It helped shield the upper atmosphere from the full effects of the solar wind. Once Mars lost its global dynamo, its atmosphere became much more vulnerable. The young sun was also more active than it is today, with stronger solar radiation and solar wind. over hundreds of millions of years, atmospheric particles were carried away into space through several escape processes. One of them is called sputtering. Energetic particles from the solar wind collide with the upper atmosphere and can knock other particles into space. NASA's MAVEN mission has directly observed atmospheric escape happening today, and its measurements show just how important this process has been in Mars's history. Mars didn't lose its atmosphere in one catastrophic event. It was gradually eroded, little by little, particle by particle, over immense stretches of time. And as the atmosphere became thinner, Mars became colder. Today, the Martian atmosphere is less than 1% as thick as Earth's, and that makes the surface an extremely hostile place. The pressure is so low that it is far below the Armstrong limit, the pressure at which water can boil at normal human body temperature. That doesn't mean your blood would instantly boil. Your circulatory system is pressurized. But exposed moisture on your eyes, tongue and airways would be in extreme danger under such low pressure. And without a pressure suit and breathable oxygen, you would rapidly become unconscious and die. Then there's the temperature. The global average surface temperature on Mars is around -63 degrees Celsius, but conditions can vary enormously. In sunny locations, temperatures can briefly approach around 20 degrees Celsius. At night, temperatures can plunge far below -100 degrees. Mars can be relatively mild in one place and brutally cold only a few hours later. And then there's another problem: radiation. Earth is protected by a thick atmosphere and a global magnetic field. Mars has neither to the same degree. Its atmosphere is extremely thin, so it provides far less shielding from the radiation environment of deep space. Galactic cosmic rays constantly pass through the Martian environment, and powerful solar events can send bursts of energetic particles toward the planet. NASA's Curiosity rover has measured the radiation environment at the surface. And for future human explorers, radiation is not a minor inconvenience. It's a major engineering problem. Astronauts spending long periods on Mars would need substantial shielding. One possible solution is to build habitats beneath the surface, or cover them with thick layers of Martian soil called regolith. So even if humans eventually live on Mars, we probably won't be living out in the open. But this brings us to the biggest mystery. If Mars once had so much water, where did it all go? The surprising answer is, not all of it escaped into space. Some water did escape. NASA's MAVEN mission has observed the processes that allow hydrogen, a component of water, to escape from the upper atmosphere. But scientists now think Mars has another enormous water reservoir. Its rocks. Water can react chemically with minerals and become locked inside hydrated minerals in the crust. One NASA-funded study estimated that a substantial fraction of Mars' ancient water may be trapped this way, so Mars water didn't simply disappear. Some was lost to space. Some remains frozen in the polar regions and beneath the surface. And some became chemically locked inside the planet's crust. Mars didn't lose its water in one place. It lost it in several different ways. And there's another fascinating mystery beneath the South Polar ice cap. In 2018, researchers reported bright radar reflections that were interpreted as possible underground lakes of liquid water. The idea was extraordinary. Liquid water beneath the Martian ice. But subsequent studies raised serious questions about that interpretation, and newer radar observations have made the liquid water explanation even less convincing. A 2025 study found that the radar response could instead be explained by a relatively dry interface involving rock and dust beneath the ice. That doesn't completely close the case, but it means the famous Martian underground lake is now much more controversial than the headlines originally suggested. And that's something worth remembering about planetary science. Sometimes the most exciting discovery is discovering that the first explanation was wrong. So why are we still going to Mars? Because Mars may contain something Earth cannot give us: a preserved record of a planet that became uninhabitable. Earth constantly destroys and recycles its geological history through erosion, oceans, and plate tectonics. Mars doesn't have active plate tectonics like Earth. Its ancient surface can preserve evidence from billions of years ago. And Perseverance is taking advantage of that. The rover is collecting carefully selected rock and soil samples from Jezero crater and the surrounding terrain. Some of those rocks formed in environments that once contained water. Some may preserve organic molecules, and some may contain potential biosignatures. In fact, Perseverance has already investigated a rock called Cheyava Falls that contains features scientists consider potential biosignatures. But potential is the important word. It is not proof that life existed on Mars. Scientists need much more evidence before they can make that claim. That's one reason the samples matter. NASA and its partners are working on a future Mars sample return effort that could eventually bring selected Perseverance samples back to Earth for detailed laboratory analysis. But exactly how those samples will be returned is still being worked out. So the story isn't finished. We're still reading it. And that brings us back to the question we started with. Why did Mars die while Earth didn't? The answer isn't one single event. Mars was smaller. Its interior evolved differently. Its global magnetic dynamo shut down early. Its atmosphere was gradually eroded by space weather and other escape processes. The surface became colder and drier. Liquid water became increasingly unstable. And over billions of years, Mars lost the conditions that once made its surface potentially habitable. Earth took a different path. Our planet remained large enough to retain its internal heat for much longer. It maintained a global magnetic field. It retained a thick atmosphere. And, crucially, Earth developed active plate tectonics and a global water cycle that continually reshapes and recycles the planet. Mars lost that planetary feedback system. Earth kept it. And that may be the most unsettling lesson Mars has to offer. Habitability isn't something a planet simply has forever. It is something a planet has to maintain. Mars may have had many of the ingredients needed for life: water, energy, chemistry, time. And yet, those conditions didn't last. Mars didn't suddenly die. It faded. And when you look at it that way, the red planet stops being just a dead world. It becomes a warning. Because if a planet can change this dramatically over billions of years, then perhaps the most important question isn't whether a planet can become habitable. It's whether it can stay that way. If you want to see what happens next in this planetary series, subscribe. Because next, we're leaving the rocky planets behind and heading beyond the asteroid belt to the gas giants.